Hello everyone, and welcome to video number 3 for lesson 7.1, Weight and Balance Principles, part number 1. So, over the last two videos, you've had the chance to learn about two different situations where weight and balance was crucial in an aircraft setting. The first one that we talked about was Flight 5481, where essentially the weight of the aircraft was too far back. The nose tilted up, the airplane stalled, the ailerons were unable to get it level, and the aircraft spun out and crashed. And then you have this instance right here, which is a movie based on a true story from American Made, where essentially this guy almost crashes on the runway because he's not able to get his aircraft up. And part of the reason why is because his aircraft is overloaded too far forward of the center of gravity or the balance point. So again, you remember these two aircraft. A couple things to take away here. If an aircraft is overloaded, generally speaking, you need more runway for takeoff. So small runways such as this one in the middle of the forest right here, no bueno when you have way too much weight. More engine power is required, your structural safety factors are reduced, higher speed is required, your climb angle is either too high or too low, like you see in these examples. You have decreased stability, and spin is more likely to occur. So an overloaded aircraft is not a good thing, and hopefully you've seen enough examples right now to explain why. Now, this next thing I'm going to ask you may not seem related at all to what we're talking about, but it's very much related. I have a question for you, and I'm going to ask it to you and then have you give your hypothesis on the screen here. Which direction do you think the seesaw will tilt? We have a 50-pound weight that's 10 feet away from this balance point right here, which we'll call the center of gravity. And then we have a 100-pound weight that's 5 feet away from that same center of gravity on the opposite side. Which direction will this seesaw tilt and why? Go ahead, take a moment and answer the question. Thank you for taking the time to answer that question. Believe it or not, the answer may surprise you, but it's going to balance evenly in this case. And some of you may think, but hold on a sec, this is way heavier than this over here, so wouldn't it tilt in this direction? And my answer to you is that if this point of balance was in the middle, then that would be true, just like a normal seesaw. But because this point of balance has changed, you need to take into account the fact that weight and distance are both factors in balance. So we're going to learn a little bit more about this, and we're going to learn about a concept called moments. So let me take you over here for a second, and let's get started right here. Like I mentioned to you just a minute ago, a moment is essentially the weight times the distance. So if you take a look over here, the weight on this left side over here, which we're going to, the moment on this side, which we're going to call moment number 1, you're going to take your weight and you're going to multiply it by your distance. And that distance from here on out in this video, we're going to use the term lever arm instead. So if you take a look over here, what you're faced with is the moment for 1 is 50 pounds because that's your weight, and then your lever arm is 10 feet. So you have a moment of 500 foot-pounds because 50 times 10 is 500. Now if you take a look over here, the moment over here is going to be 100 pounds, that's your weight, and then your lever arm here is 5 feet, so 100 times 5 also is equal to 500 foot-pounds. So for that reason, the moment that's being exerted on this side is going to balance out the moment that is being exerted on this side. So hopefully that makes a little bit more sense to you. I'm going to give you a chance now to apply this in real life. So I'm going to focus your attention over here to this center part right here. Zoom in a little bit so you can get a better look at it. So you have a situation here where you have a 40-pound generator that is exerting 1,400 inch-pounds to this center of gravity right here. The question I'm going to ask you is, how much distance is it going to take to get this 40-pound generator to exert 1,400 inch-pounds? In inches, how much of a distance is it going to be? Well, let me put it to you this way. We already know that moment is equal to the weight times that distance, that lever arm. But we already know the weight, and we already know the moment because we have a moment of 1,400 inch-pounds right here. So what we need to figure out here is, what is our lever arm? So the way that you do that is you just do some algebra. You want to get the lever arm by itself, you're going to divide weight to get rid of the weight that's multiplied, and what you do to one side you do to the other. So therefore, moment divided by weight is equal to lever arm. You know your moment, you know your weight. Why don't you go ahead and solve this on your own and figure out for me, what is my lever arm? Thank you for solving that. If you solved that, then what you would have noticed is that you had 1,400 inch-pounds divided by 40 pounds, which is equal to 35 inches. So you have a lever arm right here of 35 inches. If that's what you got, then good for you. Let's move on over here. The truth of the matter is that aircraft are not this simple. It's not like you just have one weight on the aircraft. You have lots of weights. You have multiple bags, you have multiple passengers, you have pilots, you have the weight of different components in the aircraft, seats. So you have to be able to take this moment concept and apply it to multiple things on your aircraft. So this is where I'm going to bring you over here to a problem that's going to be a little more difficult. So what you have right here, when you compare it to this problem over here, you only had a moment that was exerted aft of the center of gravity. And again, aft means back, and then you have forward in this direction. So this is forward of the center of gravity, and this is aft of the center of gravity, or back. They use the word aft in aviation. So again, get that in your head. So take a look over here. We have a 5-pound weight that is 2 feet aft of the center of gravity, and we have a 10-pound weight that is 4 feet aft of the center of gravity, that balance point. We also, in addition, have a 20-pound weight that is an unknown distance forward of the center of gravity. What your job is to do is to figure out what that distance needs to be in order for all of this to balance. So let's analyze this a little bit, okay? We know that the sum of the moments on this side, forward of the CG, has to be equal to the sum of the moments on this side, aft of the CG, in order for the aircraft to balance. So, to put that in English terms, we know that the moment, or that weight times the lever arm of B3, has to be equal to the sum of the moments of B1 plus B2. So, the moment of B1 plus the moment of B2, these have to add up to this in order for this to balance with this center of gravity point right here. So I'm going to ask you a couple questions. You already know how to solve for a moment. Again, we learned earlier that moment is equal to weight times lever arm. So knowing that, my first question for you is this. What is the moment of box 1? We have a 5-pound weight and a lever arm of 2. Multiply those together and figure that out for me. Thank you for doing that. If you completed that question, then you would know that the lever arm, sorry, not the lever arm, excuse me, the moment from box number 1 is going to be equal to 10 inch-pounds. Actually, excuse me, it's foot-pounds. The unit right there is foot. So we know that it's 10 foot-pounds because you're just taking that 5 and you're multiplying it by 2. So 10 foot-pounds. So good. We know that much. Now I want you to do the same concept, but do that for the moment of box number 2. Go ahead. Thank you for doing that. Using the same concept that we did for box 1, you're going to know that your lever arm right here is 4 feet and that your weight is 10 pounds. So 10 times 4 is going to be 40 foot-pounds for box number 2. So again, I'm not going to write out the whole unit here because doing this in the marker is taking me forever, but we know that this is 40 foot-pounds. Now we know that we have to add up the sum of the moments on this side. So we have 10 foot-pounds plus 40 foot-pounds, and that's going to give me 50 foot-pounds. So now what we need to do is solve for the arm on box number 3. So in order to do that, we know that, and I'm going to scroll down here a little bit, we know that the moment from box number 3 is going to be equal to the weight times the moment arm. Not the moment arm, the lever arm. We know that the weight is 20 pounds, and we do not yet know the distance. That's what we're trying to figure out. That is the sum of everything we're trying to do here. So 20 times that distance is going to be equal to 50 foot-pounds, which was the sum of the moments after the CG, or the sum of the moments from this box and this box. Now that we know that, what I want you to do is figure out what is my distance right here. How many feet away from the center of gravity must I place this box in order for the whole thing to balance? Go ahead, let's complete that.